Yeah, so let's continue with the discussions on, well, still on the algebras. Um, this if I want to. Um, so there's an important concept called healing form. So we're just making jokes about the names, like Lie algebras. Lie is a sort of uh funky name. I mean, in English, and now we have another strange name called killing form, but still it's a person's name. Um, so I have a L is a complex Lie algebra. Namely the algebra over C, and then the killing form is a we say on L is the symmetric bilinear form defined by this expression. So it's denoted as kappa for any elements x, y. It is the trace of joint action x and then a joint action of y. So for any x, uh, y in L. So first, this is associative. In other words, kappa x y z commutator is equal to kappa x y z. And for the some uh, special families of the algebras, namely the solvables and the semi-simple ones, the killing form have some special properties. So um, this is called, so the first one is called Cartan's first criterion, which says L is solvable if and only if the killing form is zero for any x in the algebra and y in its derived algebra. And then we have, okay, I should write it. Cartan's second criterion, um, which says L is semi-simple if and only if kappa is non-degenerate. In other words, um, kappa of we say kappa is non-degenerative. So if kappa x of y is zero for any y in L, then x is zero. So this means it's degenerate. Or as a matrix, this means the determinant of kappa is not zero. So that's the killing form. We'll use a little bit in the classification. So to complete the classification, we need to expound the structure of a Lie algebra in a sort of a more detailed way, which is called the root decomposition or root space. So let's start with an example. So again, let's use our favorite example, SL2. So remember, this is the okay. And let me just write it in.
SL2, same thing as SL2C.
Yeah, SL2C. Yeah, so most of the time I would just say SL2, which is SL2C. So writing a slightly different way, I mean it's the same thing, but it's the sum of the direct sum of the three things which we've seen before, which are called H, E, and F. And let's define this part. We call this H. So based on this notation, you might guess that this is the Cartan subalgebra, and yes, it is the Cartan subalgebra. So if we just recall what we've written down before, H E commutator is 2E, HF commutator is minus 2F, and of course, HH commutator is 0. So we can so we have these coefficients. This is like 2, minus 2, and 0. So we just write it as this way, which is I'll just use L. So L0 plus L2 plus L minus 2. Well, this L0 stands for this H, or this space spanned by letter H, and L2 is for this span E, and minus 2 is span F given by the coefficients here. So in the slightly fancier way, we can define something called mu in H star, where this H star means the space of maps from H to C. So it's kind of like the dual vector space, and such that mu acting on H is 1. So now, I mean, these three commutators, I can just rewrite it as H of E is 2 mu of HE, and HF is minus 2 mu of HF, and H, of course, commutes with itself. So now I can draw a line with the origin, and this is 2 mu, this is minus 2 mu. So basically that's, I mean, I just take this here and minus 2 mu here. In other words, I can draw it as a diagram like this, which stands for 2 mu and minus 2 mu. So this is called the root diagram. So in this example, it seems a bit redundant. It's like to write down this sort of mu in the dual space and to just like say introduce this minus 2 mu and 2 mu. It's not really, well, it doesn't seem to be really necessary, but let's go to the next example, which is slightly more non-trivial, which is of course then SL3. So these are just 3 by 3 traceless matrices. So I'm gonna choose a basis. I need to write 0, 1, 0, 0, 0, 0. F1 is 0, 0, 1, 0. H1 is so if you look at, well, it's not complete, but if you look at these 3 generators, we find that on the up left corner, we have the SL2 triple. I mean, SL2 triple. So this gives a sort of SL2 subalgebra inside this SL3. Then I can have more. I mean, of course, I need more to get SL3. Zero, 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 1, 0, 0. And then you might expect 3 more generators, but no, we only need 2 because the other one, I mean, anything else from in this Lie algebra is fully determined by these 8 matrices. So in other words, this is an 8-dimensional representation. So now I can again do the similar thing as we did for SL2. So now we say H is the span of H1 and H2, which is the Cartan subalgebra of SL3. Then I can write down all the commutators, which are just like well, of course, H1, H2 commute, and I have H1, E1, because this is okay. Let me just write it this way. I hope you can understand this, but for F1, it's just minus 2F1, and for E2, this is minus E2. For F2, it is F2, and for E3, it is E3. F3 is minus F3. Maybe I should write it there. Likewise, for H2, on E1, I have minus E1, and F1, I have F1. E2, I have 2E2. F2, I have minus 2F2. And then E3, I should have E3. F3, I should have minus F3. So now I can write yeah, maybe SL3 as the following decomposition. First I have H. Then I take the direct sum, of course, for span of EI from I from 1 to 3, and I from 1 to 3 for Fi. So this is 2-dimensional because I have H1 and H2. And this, now in terms of this mu I, now I have to define two mu's. In other words, mu I Hj would be delta Ij. So this will just be 0 mu 1 plus 0 mu 2. And here, again, I just take the coefficients in the commutator. So for E1, what I have is 2 mu 1 minus mu 2, because it's 2E1 for H1 and minus E1 for H2. And then for E2, I have minus mu 1 plus 2 mu 2. And for E3, I have mu 1 plus mu 2. Likewise, for F1, I have minus 2 mu 1 plus mu 2. F2, I have mu 1 minus 2 mu 2. And F3, I have minus mu 1 minus mu 2. Now I can plot similar roots diagram. So I can erase this because we already have this abstract notation. In the sort of mu1, mu2 coordinate system. Well, actually, they have grid on the board, so I should follow actually. Uh, I'm not sure if you can see, but I just um. So this is the origin, and for I don't have to look at it, I can recommend notes. So 2 mu 1 minus mu 2, so this is E1, and then F1 is minus, okay, it's just the opposite, so this is F1, and then F2 is minus mu 1, so F2 is mu 1 minus mu 2, and E2 is minus mu 1 plus plus mu 2, and then also have E3, which is mu 1 plus mu 2, and minus E3, minus F3, which is minus, no, F3, which is minus mu 1 minus mu 2. Then I can just connect these points as a convex hole, as a polygon, which looks like this. So what I have is a hexagon. Right here. But this is not regular. It's not it's just people like regular polygons, so it's not regular. So this is because it's not in a sort of nice spaces. So let's take a different element from the Cartan subalgebra, which is called little h3, and I define it as 1 over square root of 3 times h1 plus h2, which is explicitly this diagonal matrix. Then I can take the commutator. Of course, h1 would commute with h3, and then here I just need to rewrite this. So this is h3 with E1. What I have is 0, and F1 I also have 0. For this I have square root of 3 E2, and this is F2 is minus square root 3 F2, and this is F3 I have square root of 3 E3 and minus square root of 3 F3. So this is in other words, this is 0 mu 3, 0 mu 3, square root of mu 3, minus square root of mu 3, etc. So now I can, yeah, let me just erase this. Should be clear. Now I can just draw this in the mu1, mu3 coordinate system, and this is, it turns out this is something I should write it. Honestly. Okay, it's regular. I'm just bad at drawing this, but this is a regular hexagon. So this is F1, E2, E3. And this is the root. Now I have the oh, mu 3 is just again mu I hj being delta ij. So if I start with h1, h3, that's the mu's I would choose. So yeah, it's the same as, so I just replace h3. I just replace h2 with h3. So okay, maybe I should do this first and then draw the So this is the root system. And in particular, we can see that there are this line here, this line here, and this line here. So each circle gives me an SL2 root system. So means it contains SL2 as a subalgebra. So more generally, I have the following definition, which is the root space decomposition, which is denoted as this. They're labeled by alpha, where L alpha is the set of elements in this Lie algebra such that h of x is given by this thing for any h in the Cartan subalgebra. So for example, here this alpha h here it's just this 0 mu 3, 0 mu 3, square root mu 3, etc., etc. So this is called the root space. And in particular, h is L0 because everything commutes, so it's just 0. So this is alpha h is just 0 for this Cartan subalgebra. And this phi, where for the sort of range of the alpha is called the root system. And alpha is called the root. So in other words, here I have these 6 alphas. Right. So a very important proposition, maybe I should write it down, proposition, is that given the root alpha, then L plus minus alpha are one-dimensional. They are both one-dimensional. And the only multiples of alpha, which lies in the root system, phi is plus minus alpha. Yeah, so in other words, if I have, say, C alpha also in the root system, then C is plus minus 1. So a corollary or like an obvious consequence is that the dimension of the Lie algebra would be the dimension of the Cartan plus, I mean, of course, I mean, that's you take the sum of the root system and dimension of L alpha, and this is equal to the size of the root system, which is even because you have plus minus alpha. And in fact, yeah, I'll just write that proposition. There exists a unique, just write it in words. There exists a unique element called T alpha in the Cartan subalgebra. associated to each alpha in the root system. So it's labeled, so this T is labeled by the subscript alpha such that the killing form of T alpha and K is equal to alpha K for any K in the Cartan subalgebra. So, and also, our SL2 has been our sort of favorite example because it is useful in this sense for any alpha in the root system. So for any root and an element X in L alpha, then there exists an element we call Y in L minus alpha. Okay, it looks like subscript L minus alpha, such that we have the subalgebra which we denote as SL of alpha given by the span of X, Y, and the commutator. This is a such that this is a Lie subalgebra of L, and SL alpha is isomorphic to SL2. So now we can just rewrite, use a different notation to call this E alpha, this F alpha, and this H alpha. And this is, and also, in particular, alpha of H alpha is 2, but that's not really important here. The important thing is now we have the three generators, and this is why we call this SL2 triple, because in the end, everything, the Lie algebras can be written as an algebras with certain generators, which are given by these EFH and the relations among these generators. So this is called sort of the Chevalier generators, and we'll talk about this later because the whole root system and like all the elements in the root system, each would give me sort of like each root will give me an SL2 triple, and that's a bit sort of too much because I don't need that many generators. But anyway, there is a sort of identity which says P alpha is H alpha or the killing form of E alpha and F alpha. So if you like, you can take this as the definition of T alpha. Then we can also translate the killing form into a non-degenerate symmetric bilinear form on the root on the roots. So well, I'll okay, let me just write this on the roots, which is alpha beta for any two roots. It's defined as kappa T alpha T beta. So if you like, this is just the usual inner product of your vectors, and
This terms are the space generated by the root system.
the root system. Yes. So each alpha is the yeah, I've just raised it, but yeah, because alpha is just the space of X in L such that, okay, I'm just rewriting it. So writing this again, but it's just this thing. So each L alpha is associated with a root. So that's why it's called root space decomposition. So yeah. So because they are vectors, so I have something called reflections on the vectors. So in other words, SV will denote this as the reflection in the hyperplane normal to a vector V. So in other words, SV would do this operation. So it sends V to its opposite minus V because it's a reflection. And of course, SV on say Y is equal to Y for any Y which is perpendicular to V. And in fact, one can check that SV of X is equal to X minus 2X V over V in the product times V for any X in the root system. And for my root system, this S alpha generate all the S alpha, they would generate a group, a finite group. And this is called the Weyl group. So it's just the reflections on your roots. And also just on shorthand notation, we use this bracket to denote this thing here. So it's just shorthand notation. But notice that this is only linear with respect to X, not linear with respect to V because of this thing here. So there is a finiteness lemma which tells me that the thing, I mean, this thing or this thing here is always finite. So it's called finite. And it's lemma, and in fact, it really restricts the possibility. So if I have a root system and I have 2 alpha beta in the root system, okay, maybe I should, yeah, okay, I'll just use 5, but there's for alpha not equal to beta, not equal to plus minus beta, then this alpha beta, beta alpha can only take value in 0, 1, 2, 3. So now I can just list all the possibilities for the root system. So I have, this is not symmetric because of that definition, and theta would be the angle between alpha and beta. So I just write a theta, and also I can write, so I can compare the inner products. So the possibility, first of all, is 0, 0, and they will be perpendicular. And this is undetermined because it's 0 over 0. And then I also have 1, 1. This will be the group pi over 3. This is 1. And also have minus 1, minus 1, minus 2 pi over 3, 1, 1, 2 pi over 4, 2, minus 1, minus 2, 3 pi over 4, 2, and 1, 3 pi over 6, 3, minus 1, minus 3, 5 pi over 6, 3. So that's the table of all the possible combinations. And also, because I was saying we have this SL2 triple so that we can rewrite our algebra using the SL2 triples, but there are too many. I mean, of course, it's sufficient, but but there are sort of too many generators. I don't need that many, because this is sort of related to the concept of simple roots, which is a subset of roots. So a subset, well, of the root system, let's just write that as B, is a base. Well, first of all, B is a vector basis. And secondly, for any beta, for any for any root beta, it can be written as beta equal to the sum of k alpha with the sum over alpha in the space B, with k alpha being an integer. And all the non-zero k alpha. I mean, of course, some of the k alphas can be 0, but all the non-zero ones have the same sign. So either they are all plus or they are all minus, except the 0 ones. So theorem, every root system has a base. So this is always possible. So I can always find a set of alphas such that I can have express any roots like this. And because k alphas have the same sign, so if k alpha is they are all non-negative, we call it this is the positive root. We call them the positive roots. So for beta, maybe I should write this like this. So this is beta is a positive roots, and we denote the set of positive roots as, well, 5 plus. And if it's negative, of course, they're called negative roots. And this alpha, this set of alpha, they are called simple roots. And of course, the root system can be decomposed as a disjoint union of the positive and negative roots. And the corresponding y reflection, they will just be called simple reflection. So that's and in particular, you can get the whole root system using the reflections. So now we are ready to write down all the possible or the classification of the simple Lie algebras. What we need is something called, okay, there is we can just encapsulate every sort of the information we need in something called the Cartan matrix, where the size of this Cartan matrix is equal to the number of simple roots, I'll just write it as alpha. Okay, maybe I should say alpha 1 up to alpha L. So it's an L by L matrix, and this L would be called the rank of G. Rank of L, I mean the Lie algebra L. And this matrix is A, which is of course Aij L by L, where Aij is this bracket alpha I, alpha j, we've seen before. So for example, we have the simplest example we can have is this L by L matrix. So it's this 0, and it's just 0. I mean, know what this means. And 0, minus 1, 2, dot, dot, dot. So it's this matrix. So it's diagonal. All the diagonals are 2, and the next two like off diagonal parts are all minus 1. So that's one example. And of course, you can have those non-symmetric ones as well. And the Cartan's classification, so this is the theorem, which is called Cartan's classification because Cartan classifies this in his PhD thesis, which says the Lie algebras can be classified by the so-called thinking diagrams, where the vertices corresponds to the simple roots. And then I can draw edges or arrows connecting these simple roots. So suppose I have, so the lines, if I denote as, I don't know, say D alpha beta, this is equal to this thing here, the thing we've just seen in the finite, this lemma. And if the alpha beta is greater than 1, this means alpha and beta would have different lengths. So, and of course they are not orthogonal, namely I mean, of course it's not 0. So we just draw, have an arrow. So we put a direction on this on these multiple lines. We say this is an arrow from the longer root to the shorter root. So it's something like this. So if alpha has larger inner product than beta, we say it's a longer root. So the list now of all the Lie algebras, simple Lie algebras, and of course complex simple Lie algebras, there are 4 infinite families which are called classical. One is denoted by an with n greater than or equal to 1. So that's the thinking diagram with n vertices. Maybe I just run inwards. N vertices. And this is the Cartan matrix over there. So in fact, this is Sm plus 1, namely all the traceless matrices. Then I have Bn with n greater than or equal to 2. They look like this. So there is one short root in the end, of course, always n vertices. And this is denoted as SO n plus 1. which says the matrix X, its transpose is equal to minus X. In other words, it's antisymmetric. Cn, which with n greater than or equal to 3, it's sort of like the other way around. So I have this thing here, and this is called SPN, SP2N. Sometimes people would just denote it as SPN. So here you still have n vertices, and this satisfies this relation, where omega is the matrix as this. So it's a kind of like a block matrix with 0 here and identity matrix here, minus identity matrix here. So it's always size 2n by 2n. So it's always SP2n. And then I have dn, which are n greater than or equal to 4, which is something like this. So it has a bifurcation, but all the roots have the same length. So oh, yeah, this is 2n plus 1. So again, I have n vertices because the rank is n, and this is SO2n. So it's the same definition there, but that one is of odd size. This is of even size. Okay, it's a bit weird to split here, but we also have some sporadic cases, which are called exceptional. That denote as E6, E7, E8, F4, G2, E6 is this, and E7 and E8. So okay, we can. So this is 6, 7, 8, F4, and G2. So also, if you're curious about the dimensions, this is n plus 1 squared minus 1. This is okay, maybe let me just write it write it here. So SLM plus 1.
So of n corresponds to inner space.
No, it's called symplectic. So we'll say something more when we talk about Lie groups. It's the word symplectic. Yeah, I'll write this down later. So just actually, for spin, it's actually more related to the SOs, but we'll see when we talk about Lie groups. And SO, well, I'll just use n. This is n times m minus 1 over 2. So this is the dimension. And SP2n, it's n times n plus 1. And for the exceptional ones, 6, 7, E8, they are 78, 133, 248. And also I have F4 is 52, and I have G2, which is 14.
Is that dimension about Lie algebra, not
yes.
the dimension of
yeah, the dimension of the Lie algebra, yes. Yes. So yeah, so
that's different from our dimension of representation.
right, that's different. I mean, you can have representations of various dimensions. Like the fundamental representation will have this dimension. And what do I want to say? Yeah, if you check the for these simple Lie algebras, you always have the determinant being positive. of the Cartan subalgebra being positive, Cartan matrix being positive. Also, there are a bit more terminologies. So let's see, I can probably skip a little bit. Yeah, so we said you have the root alpha, and sometimes we can define sort of the co-root of a check, which is given by 2 alpha over alpha dot alpha. And also there is something called the fundamental weight. So lambda I, so it is a sort of covect. It spans the covect space of the co-roots, but we can just write it as for any root, we can just express it looks quite similar, but anyhow, that's so for any root, simple root, any simple root, I can always use the fundamental weights and the Cartan matrices to express the simple root. And there is so the integer span of the root is called the root lattice because it's a lattice. And also I have co-root lattice spanned by co-roots. And then I have the span of fundamental weights. These are just called the weight lattice. Right, so now I have a theorem going back to our SL2 triples. So for any semi-simple the algebra L, I can always with simple roots, well, simple alpha I from say I from 1 to L, it can be always presented using the following 3 L generators. E alpha, yeah, okay, I'll just write EI means E alpha I, and likewise Fi, Hi with the relations of course, H, they are Cartan subalgebra, so they commute with each other. And Hi, Ej is equal to Aij, the Cartan matrix Ej, and Hi, Fj is equal to the minus Cartan matrix element Fj. And also I have Ef. This gives me delta Ij Hi. And so maybe I shouldn't break the on here, but there's another set of relations, which is okay. Maybe I should write it over there. It's just too low. So that's the relations continued. 1 minus a j I e j 0. So in other words, I take of course for I not equal to j. Because so I just take in that many commutators so with EI and EJ, and likewise, I have another thing for F, which is exactly the same, but replace everything using this, and also I not equal to J. These are called cell relations. So basically, now given the set of triples, I have the relations among H's and HE's, EF's and EE's and FF's. So that's sort of some presentations or ways to express the algebras that are also very often used in their sort of generalizations. I mean, the generalizations of the Lie algebras, etc. So recall, yeah, we still have it here. So we have the weight lattice, which is given by Ni. Maybe I should write. I shouldn't be lazy. So this is the weight lattice, where these are the fundamental weights, and I can define something called lambda with lambda I with null with Ni being non-negative. Okay, I just wrote in the weight lattice. This is called a dominant integral weight. And there is a theorem which says that every finite dimensional irrep is of a simple the algebra is given, well, it's in one-to-one correspondence with this dominant weight, so with the lambda, little lambda. So in other words, when we write down this vector, we are referring to one representation of the Lie algebra. So in fact, we can decompose so I have a representation or I mean an irrep or module M, so I can decompose it as the so-called weight space weight space decomposition. So such that H alpha acting on an element VW is equal to W alpha VW for any VW in the subspace MW, and this vector W alpha, so I just write alpha from 1 to L, i.e. W, yeah, I think you understand this. This is called the weight of the module. They are called the weights of the module of the module. I mean, it's the same instruction. So in particular, for the highest weight, so there exists a highest weight, which is exactly given by this little lambda, the dominant one. E alpha acting on the vector is 0, so it annihilates this, and this is called the highest weight module So in other words, everything is a highest weight module. For example, well, let's just take now. Let's just take SL3. Say, well, the Cartan matrix is this. So, and alpha I is this lambda J. So now I have two weights. So alpha 1 is just 2 lambda 1 minus lambda 2. Alpha 2 is just minus lambda 1 plus 2 lambda 2. In other words, this I can write it as 2 comma minus 1, and this I can write it as minus 1 comma 2. So let me write it over there. So I can just generate the weight lattice. So in the basis of okay, maybe I don't have to draw this, but just an example. So if we choose, say, lambda equal to W1, which is essentially 1 comma 0, then we get the representation just by, so that the whole space is given by minus alpha 1. So it's minus 1, 1, then minus alpha 2, 0 comma 1. So that's the weight space decomposition, and this representation is usually just denoted using its highest weight, which is 1, 0. So you might wonder why I only have these three, not like lambda minus, say, alpha 2, etc. This is because okay, maybe I shouldn't write. So it's lambda 1. So all the weights should contained, they are contained in the convex hole of the orbit of lambda under the Y group action. And so just under the Y group.
What is exactly our weight and what's the difference between the loss and the weights?
So weight is so here I'll just okay, I think I've erased it, but I just say so for any root we have, I just define the weights to be this. So this is the root, and this is the weight. Well, in fact, it is a you can think of this as also as a sort of, well, I shouldn't say covector, but it's sort of a dual vector space such that lambda j ai check is equal to delta ij. So, but again, because it's finite dimensional, so the dual vector space is isomorphic to a vector space, but whichever you like. So here I would just say this is every alpha I can be written using the Cartan matrix and the weights, and this is, you can take this as the meaning of the weights. Yeah, so for example, I have, well, I know I have some letters. Okay. Okay, it's everything is like things erased and dots I draw mixed. So for example, just I have some random weight lattice and say I don't know, this is, say, lambda being the highest weight, then I always have some Weyl group action which which would take me to all the possible vectors under this while group action, and all these vectors will be restricted in this some convex hole, sort of this polygon, and everything inside this, all the weights inside this representation should be contained in this thing here. So that gives all the possibilities. And this is this 1, 0 is the fundamental representation. So this is the fundamental representation. And likewise, when we take lambda to be 0, 1, this is the anti-fundamental representation. And this is given by this set. So yeah, and also there was another thing I don't want to write down all the weights, but I can just give you the highest weight, which is just right here, lambda 1, 1, and this is the adjoint representation. So in general, well, for AN, namely SLN plus 1, this is the fundamental, and this is the anti-fundamental, and this is the adjoint. So yeah, okay, I guess I can give you one more example. So for Dn, because the roots, the simple roots are associated with the fundamental, sorry, the vertices in the thinking diagrams. So if I take for example, this is 0, 0, 0, 0, and this is 1, this is 0, so I can write this as 0, 0, 0, 1, 0. This is spinor representation. And also I can swap these two. So I can have 0, 1 here. So that's another spinor representation. So we say this is chiral because I have sort of two choices. While for Bn, this 0, 0, 0, 1 is the only spinor representation. Yeah, so in the like last 22 minutes of the second session, finally we're going to talk about Lie groups. So someone's also asking me about the Lie algebras and like the relations between Lie algebras and Lie groups, why they are all named after Lie. So roughly speaking, so G, okay, not G, I'm using L. The Lie algebra is the tangent space of the Lie group. There's G at, well, actually at the identity element. So so what does this mean? Well, of course, I mean, for L being a tangent space, this is fine because we know the algebra is a vector space with extra structure, so it makes sense to be some tangent space. But for G, I mean, what does it mean, the tangent space of G? This is because we have the following definition. Lie group is a group which is a manifold. So yeah, so a Lie group is so that's why we say it's a sort of pictorially we just have a Lie group which is a manifold. I have the identity element, and this is your Lie algebra, which is this tangent space. So by the way, so a little aside, which says so if we drop the antisymmetric condition on the bracket, this is not Lie algebra anymore. It's called the Leibniz algebra. And the problem of finding the corresponding group, finding its sort of corresponding Leibniz group, is something called Consigue problem, which is a French word. So I don't know who came up with this name, but this word originally means some like imaginary creature as an embodiment of absolute absurdity. So it means something very absurd. So, but anyhow, this is an open problem, I believe. So yeah, it's just some other, yeah, not really related to our main topics, but I just want to mention here. So examples of Lie groups. U1 is the simplest one, which is this e to the I theta for 0 to 2 pi. In other words, this is a circle because it's just going around. And then SU2, this is the second example. SU2, which are the matrices, 2 by 2 matrices. Of course, we determinant non-zero, but here it's even more strict. So, which says M dagger M is the identity, and determinant of M is 1. So this is S means special, U means unitary. So we can parameterize this as, well, of course, A, B minus B star, A star. Because determinant is 1, so we know it's A star plus B star is 1. And you can check that indeed M dagger M is the identity of you ever know. So if we write A as, because they are complex numbers, so I just write as usual as x1 plus ix2, y1 plus iy2, then this condition, the determinant condition, becomes x1 squared plus x2 squared plus x3, y1 squared plus y2 squared equal to 1. So this means SU2 is actually a 3-sphere. So now there's a closely related Lie group, which is called SO3, which are 3 by 3 matrices, but real matrices satisfying M transpose M1 and determinant being 1. I mean, of course, because I define it as a real matrix, so this is the same as M dagger M being 1. So sometimes I may just write M dagger M being the identity just to sort of make the notations look more look the same, but they're the same thing because I'm dealing with real matrices. Well, so to understand this is sort of as a manifold, let's first relate it to SU2. So we start with the matrix x y plus rz, y minus rz minus x. So if you like, this is x sigma 3 plus y sigma 2 plus z sigma 1, well, your sigma i's are the Pauli matrices, but I don't have to, but that's the expression anyway. In other words, it satisfies v dagger equal to v, and the trace of v is 0. So we now act on v by our SU2 Lie group by this action, taking the conjugate m dagger v m. So one can check that. I think it's, yeah, I don't have to actually show this, but you can easily find that SU2, we say SU2 preserves v dagger equal to v. So okay, so yeah, let me just call it v prime. And trace v being 0, of course, and also the determinant of v. In other words, under this transformation, I would still have v primed dagger being the same as v prime, and trace v prime is still 0, and determinant v primed is equal to determinant of v. So that's some straightforward calculation, but and then yeah, in view of time, let me just skip the details, but this actually induces an homomorphism from SU2 actually to SO3. So if I write the map, okay, I'm calling this A, but I hope it's fine. From R3 to this all this set of these matrices V, and also which is basically yeah, maybe I should so basically sending x equal to x, y, z to the to that's okay, maybe I don't have to. So it's sending this vector x, y, z to that matrix. And also I have another map which is an homomorphism from the space of all such matrices to itself, which sends V to the V primed I've defined here. And this would give me a homomorphism from SU2 to SO3, which is given by so if I have an SU2 matrix M, then it will be sent to, so this homomorphism is given by such sequence of maps. So first A and then compose it with Tm and then A inverse. So this is a homomorphism from SU2 to SO3, but this is not an isomorphism. Because remember the action on V is, well, M dagger Vm is V primed, but also this is equal to minus M dagger V minus M. In other words, this homomorphism is onto but not one-to-one, because M and M, they are sent to the same element in SO3. So if I have a 3 sphere and I have as SU2, SO3 is kind of identifying the two opposite, namely the antipodal points on your S3. So it's just with the and typical points identified. So in other words, there is a subgroup, normal subgroup in SU2 such that SO3 is the quotient. Well, I just start three sphere quotient by Z2. Well, this Z2, what it does is just to identify all the opposite points. So now we have classified the algebras, and we want to classify the Lie groups. But this is a bit too general. Well, let's just focus on compact Lie groups. Well, in fact, there's no classification of non-compact Lie groups. Well, there is a family of non-compact Lie groups which are related to the nilpotent Lie algebras, but in general, non-compact ones are not classified. So there is a theorem called Peter-Weil theorem, which says that any compact Lie group is isomorphic to a subgroup of a unitary group. So by unitary group, I mean the matrices satisfying M diagram. So yeah, then so unitary matrices. In other words, compact Lie groups are matrix groups, so we can just work with matrices. Well, for example, I mean we have SU, which further has the condition determinant M being 1, and also we have SL and maybe now I should write, yeah, SN, L, and C, and also SN, L, and R with the matrices of only with, okay, I mean, here, of course, I have M diagram is 1 as identity. Then here it's just the determinant being 1. And also I can have ON or SON, which says the transpose is it's antisymmetric. So if we consider UN acting on a vector in Cn with this action, so for each component Vi in this vector V, I just send it to Mij Vj, and likewise I can also say consider On acting on a vector Rn again with this. Then one can check that V is preserved. In other words, V remains the same after this action. So here again, dagger depends on whether it's Cn or Rn. So it's just transpose when it's Rn. So it preserves the length of the vector. Or more formally, we can just write this using some sort of metric. So, which is this Vi delta Ij, Vj, for either V in Cn or V in Rn, depending on the case we're talking about. So in general, GVW can be written as V dagger IW, where I is the identity. Then we say the matrix, so UN or ON preserves G. Yeah.
Class 2:30, so can you wrap up?
Yeah, okay, I'll stop in 5 minutes. Yeah, okay, 3 minutes. Okay, I'll stop. Just finish the sentence. So, which means M dagger GM is equal to G. This dagger is transpose for real case. So, so I'll stop here. So next, I'll introduce symplectic ones using the similar method. Okay. Yeah. Okay. Just yeah, whatever do.
Are there any quick questions?